Okay, so first of all, thank you for this opportunity. I can explain certain parts about the hardware and how C++ plays a role in the hardware modeling part. So it's like, and if you think hardware, right, how language something as C++, which I mean, it's primarily on software front, plays a role. Maybe I'll try to cover. And if anybody here who is already aware about hardware modeling a bit, I think there is one or two things which might be interesting for you, even if you are an expert in it. The thing is, when we are in expert in it, certain things we take at a face value that okay, this works, and then we don't have to go in much detail. But because I'm trying to focus in this talk more towards starting from a very basic and scratch, that how we will do it and why we will do it, maybe it will become interesting for somebody who is already expert in this too. So, as Ankur mentioned, I am currently working in Intel as a platform architect, and my role is to do some system level analysis on performance aspect of it. So, we'll cover more what is this performance aspect, etc. In this talk. So, let's get started. As part of today's talk, as you can see on the agenda screen, I'll introduce you guys to the hardware and hardware modeling, how what hardware description language is, and why we not opt for it and opt for C++ over there. And in order to use this C++ in the hardware context, how a C++ based system, which is an open source project called System C, helps us in moving forward. And we'll show some examples around them. We'll take a bit deeper in the similar context, that how System C has evolved and how we are using it. And then certainly I'll take it even further for few parts of this TLM. You don't have to worry if you don't know what this is, but we'll take it forward like that. And then at the end, I'll show some real application and try to explain how this guy helps achieving certain things. So with this, let's get started. And of course, if you have any query, questions, or you want to add something, please be my guest and interrupt me anytime. Okay. So let's start with what is basically an hardware, right? So the hardware in this context is any integrated circuit which you see in the, let's say, in the mobile chip, in the laptop's chip, a PCB, right? Any chip you see, any ASIC you see, which is an application specific ICs, or you see FPGAs. FPGA are field programmable gate arrays. We don't have to go much detail into it. I just want you guys to have aware about this terminology, which is for hardware. So any basically an integrated circuit is an hardware for this context, and it is actually fabricated on a silicon with billions of transistors. So these transistors are the one which drives from 0 to 1, 1 to 0, and try to hold those values, and then the whole hardware is actually built on top of them, let's say. For creating such hardware, the code which is written is typically in hardware description language such as VHDL or Verilog. So these languages are primarily targeted for giving you the syntaxes and the body or infrastructure to write hardware effectively, and then later we'll see even the whole process, how hardware gets started till the manufacturing part. But yeah, these are the couple of languages which at least I am aware of, which are used for writing the hardware. And if you see, in this today's talk, we are of course talking about hardware modeling. So we are ultimately trying to mimic something which is doable in hardware, but we are trying to mimic something in some other language. So that poses a question, that why we want to do something like this. The reason is mostly the time. Why I'm say this is, let's say, if you see in the first diagram, the traditional hardware software design flow. So we start with the architecture of, or specification of an given hardware, that okay, we want to build a hardware which looks like this, which will be bumped into, let's say, a designer which will write a code of that hardware. Then it will go to a verification guy who will verify whole hardware, that okay, these are the intention behaviors, whether they are met or not. Then the process of actually manufacturing it on the chip, on the actual hardware starts. So up to here everything is in simulation, but that is in a still in the RTL world. And then once the hardware is available, let's say you can run your embedded software on top of it. Now, because I have worked a bit on RTL verification, I can tell you, even parallelly to this physical design and hardware manufacturing, you can run embedded software once you have a something stable on RTL design and a better thing on RTL verification. There are many aspects of verification, such as IP level verification, a SOC level verification, and a system level verification. So here, which we are talking about embedded software, usually stands at the system level. So now, in order to build a software like that, your system should be up slight bit so that it's not going down the drain. Whatever effort you are putting is making sense. But this RTL designing and RTL verification is many months process. So when you start designing, let's say it takes 5 to 6 months to design something with feedback of RTL verification, it will take might take 8 to 10 months, let's say, and then you have something ready where you can run software. Not everything, be aware. But imagine that as part of this designing process, when it is going on, you could very quickly write an hardware model which is nowhere near to the actual hardware with respect to all its accuracy, but it is serving a certain things which are essential for your software development. So over there it is pretty accurate, and even if it is not, you can always feedback to the architecture and get it fixed. So if you have a model something like this, your development cycle of embedded software or early exploration will start way early than your traditional flow. So this gives you that shift left in the overall process that can give you either certain feedback or information very early in the stage, or can start your development pretty early so that when the hardware is available, you are not starting once after that much time. So this is kind of a parallel flow, and this is why the hardware modeling exists. Now if you see in the real world, do we do this? We start exploring something early even before we finalize? Yes. Let's say you go to buy any 2 bhk 3 bhk flat, you will do your own study, right? You will see that whether it fits your need, whether you want to configure, how much sunlight you get, how much let's say if you do some furniture, whether the enough space would be left or not in your flat. We do this all the time. Same goes for marriage. You try to marry someone, you don't directly marry. Try to see whether you are compatible, what changes you need in her, what you changes you will do in yourself. So this kind of thing always exists. The same goes for hardware modeling. It's about before committing something, you want to make sure that things work, or if you want to change something, you can change. Good till now? Okay. So let's move to why we use C++ and not Verilog or VHDL, which I already explained. So this particular slide, it's still bit debatable. So these are what I understand that why we use C++. See, as I said, these hardware models are expected to be written quickly, and hence we will write them at higher abstraction levels. Now, uh, if we want to do it at in Verilog or VHDL at higher abstraction level, it will still be tricky. And then I don't think so. It's just the one point which helps us go in C++ direction, but all together. So if you see the second point where compilation time and simulation speed comes in picture, compared to Verilog and VHDL, C++ code will be compiled very fast, and I mean depends on which kind of code it is, but yes, it will compile bit fast. And with respect to simulation, for the fact I know that one of the SoC where we were trying to bring up Linux used to take almost 45 minutes to 1 hour. Initial 20 minutes would go in reset itself, but if same SoC I tried to bring up in C++ world, it used to happen in few minutes or seconds. So this also plays a role. Then if you see in our primary use case, we are trying to bring up this embedded software. So the developer or user's familiarity is already with C based environment or C++ based environment. So your stakeholders for doing this modeling if they are aware about what or how to debug, how to look into code, it helps. On top of it, C++ provides us very uh, flexible infrastructure for us to write complex models. Maybe we won't see complex models today, but I'll try to explain one use case where having a pointer in C++ solves many things in hardware. And the last is this Verilog and VHDL is usually intended for timing level accuracy and synthesizable code. And if you think like that, somebody who is expert in Verilog or VHDL, why would he write a code which is not going to turn into an hardware, right? It's like somebody is very good at constructing a building, but all you want them to construct is a model house. They are going to run out of patience, right? So I think that also plays a role in going towards C++, but majorly C++ is there because of its speed and flexibility, and then somewhat on the familiar environment. Okay, so let's jump into somewhat hardware. So if you see, this is an example sock I took from some snip from online. Yeah, anyone saying something? Okay. So if you see, this is an example of an any hardware. If you see this block, this would be a processor. But what I want you guys to look at is this particular small this block, right? If you see this one, this is a crystal oscillator. This is the guy responsible, let's say, for generating your clock. So if you see any mobile laptop, you'll say that okay, it is running on this many gigahertz, or it is running on this speed, right? So this guy's responsibility is to generate that clock. So this clock is supplied to each and individual hardware block within the SoC, so that they can run in a tandem with the clock. So hardware, usually every block will run with this cycle level accuracy. When I mentioned timing accuracy, this is what I meant by hardware. So first thing is this clock, right? Second thing is, you see all these are wires, right? So their job is to supply information to the other guy. So let's say this guy is responsible for something, will perform that calculation, and then will supply the information which will be needed by other block. They'll use it and perform its own calculation, right? And third thing is, all these individual block you see, they are not dependent on each other except the interface, and they have their own functionality to be done. So if you see in general the hardware, right, there are three things which we want to look at. First is clock. Now, how clock looks is, it will go from 1 to 0 and 0 to 1. That's what clock is, right? You will have a clock period which will transit like this, 1001, right? Then second thing what we saw was wire, let's say signals. So how we transfer the information from one block to other is, let's say, happening over clock period. The sampling of those values will happen over a clock period, let's say. So now, for such signals, for your internal processing, you want to do the processing on the current value, and then when you send that value to the other IP, it will work on the updated value. But when, it will be on the clock period. So this is what we'll try to see more. The last thing is, as I mentioned, parallel execution. Internally, a hardware block also performs many things parallelly. Same as at the SOC level, also many IPs will perform things in in kind of a parallel to each other. It's just that they will be dependent on the interface. So now, if we want to model something like this in a C++ language, right, what we need is actually a notion of time. And there are certain things, as I mentioned, how to do this signal value transfer. So let's see how system C is a C++ based system is going to help us over there. So there are four phases of this kernel which are interested for this context. First is set of runnable process, update request, delta, and time notification. We'll go in detail of each of them. So let's move to a actual code, that how it is done. Okay. So what we want to look at is how time is implemented first of all, right? Because
Ankit, can you please increase the font?
okay, let me see. I think it will going to be a bit weird, but is this fine? Should I change
Yes, this is
to?
good.
Will do. Okay.
Yeah.
So I hope it is clear that why we need the essence of time, right? And this cannot be a real time. We want to mimic based on our frequency that how the time evolves, right, or gets increased. So ultimately, we want to introduce a kind of a virtual time for the simulation, right? So if you see any simulation in system C starts with this guy, system C SC start. This particular file is an open source project, is part of system C234, I think. And yes, I'm going to present this. So this SC start usually takes a duration that how long it wants to work and what's the starvation policy. Maybe we don't go much detail into it, but the moment this particular function is called, our simulation will start, and ultimately this is the entry point of a simulation. So if you see, when the simulation start, hoping that all other things are fine, we will start the simulation from this point, that if everything is good, let's start to simulate. So this is our simulation function. Now over here as well, we'll do certain calculations, but what we calculate or what is the essence is here, that till what time we want to simulate. And then once we start the simulation, you see, this is the core of our simulation process. This is where all this synchronization and what all I talked about in hardware is handled. So we'll go through the first this block first, and then we'll enter into this crunch function where other things happen. So as soon as we enter here, there would be something called as crunch. But let's go a bit deeper, that okay, we did certain processing as part of this crunch, but what happens is this is your current execution time. So the point is that how we increase the simulation time, or when actually we increase the simulation time, right? So in this particular simulation kernel, it takes that okay, this is my current execution time, and then it checks what is the next time to do certain things. What happens is that for first time slot, let's say you were supposed to perform certain actions within your whole SoC or hardware, all those will happen. But once you are saying okay, on this clock's pause edge, whatever I needed to do, I've already done it. So this is like set of runnable processes, the first bullet point I had. Once it is done, you want to increase the simulation time to the next cycle where you find something to be done. So this is where this next time will come in picture. It will check whether do you have anything for those increase of simulation time, and will try to check whether after increasing, after reaching to that time, do you have something to be done. If you have something to be done, then it will again execute the crunch part. If you don't have anything to be done, it will again increase the simulation time by this. And then uh, this is how whole process works, that you run all the things for the current simulation time, check if you can increase the time, and over there anything is pending, then you move there, you execute that time, and then hence you go forward. So now this is just about introducing the time in our context. So we know now that how 1 to 0 or 0 to 1, that clock period, will evolve into a kind of a virtual time, a simulation time. But now let's move to the crunch part, that what happens as part of crunch. Crunch is the main core where our executions will happen. So First one is this evaluate phase, where all the execution that for this time I wanted to perform all this actions. We will register functions with this particular evaluate phase, and kind of a event that okay, we want to perform this particular function during this events. Then this is the code which will execute those events. So your function will get called, you will perform what all things you want to perform as part of that body. Imagine this as a small part of your hardware where a certain function is happening. The moment it should happen, it should enable this portion of the code will execute that function. And then this particular execution will of course make some changes to your internal variables. The second phase is where you will update those values, and this is the update phase where you will update those values. And then this is called as delta cycle. This I'll explain more when we have an example to look at, but just keep this delta cycle in the mind, that it's an important aspect of our this modeling. Now once we have the set of runnable processes, we ran them, we did update whatever they had changed the variable, we did the update, and then again we will check whether we have another processes to be run. If we don't have another processes to be run, we will increase the simulation time from the others block. So this is how uh, we ultimately uh, simulate the time in system C context. Now when I told about this update phase, this is the update phase. You see this perform update function call. This perform update is present in this prim channel. Ultimately, it calls update
Aniket,
function. Yeah, yeah.
I I think Aniket has raised his hand, so I think he has a question and I have a question as well. So I think Aniket should
Hey,
go
sorry,
first. He has his.
yeah, I don't have that. Ankur, can you interrupt me if somebody has raised the hand?
Hey, it's okay. So I think Aniket go first. He has a question. He raised his hand, and I after that I will.
Hey
Okay,
Niket,
okay,
yeah.
please.
So my question is that what about like you mentioned that if there is any process, it will run,
Yes.
and what about multiple processes which wants to run at the same time? How will the execution happens for those processes?
So if you see, right, this is well true. So you will take all the runnable processes. It's not just the one process which you run. You run all the processes which are kind of available or ready at that particular simulation time. So you take them, you run them, and you keep those evaluation handy.
Okay,
So
makes
it's
sense.
not just the one process
Ankit,
which runs, but imagine this: they run in sequential order. We mimic them, that it seems that okay, they have run parallelly, because we are in context to the simulation time. So at the same simulation time, you will see that okay, all got invoked sequentially maybe, but from the system point of view, they happened at one time only.
yeah. So, Nikit, I wanted to ask, like, as you just finished, so if we have multiple processes in the simulation time, it would be taken as a single, like, as a single multi-process thing only. But what about the clock cycle? Like, since crunch is being called from the timing section, from the clock, right? Crunch itself is being called from there.
So from here, the crunch is called, right? So this is, let's say, the first time the crunch gets called, right? So it will run certain things and it will finish in that particular time. Let's say the crunch is finished. Then you come here and you see that after executing this thing, at what time, let's say after a clock period or a 5 clock period, you have something to be done. So this particular guy will increase the time to till that point, and then again will do the crunch. Crunch is kind of a portion
Is
where all the
the
execution happens. So it will keep happening, but after a different time.
So this part is where we are keeping track of the time. Like even if crunch is doing multiple operations, so even like suppose let's suppose
Correct.
like the whatever crunch is doing, it took 5 clock cycles. So is the counter for that clock cycles, is it being update kept in crunch or is it in this method,
No, so the
in this do
crunch
loop?
won't increase the simulation time. So crunch is where your execution will happen at a given time, one time. It's this guy who will increase the time. So think of it as crunch is an internal process which its job is to perform parallel actions on or whatever is available the methods. Consider that it's 5 nanosecond currently, okay, and at 5 nanosecond you have three processes from three different hardware blocks to be performed. Crunch will call at 5 nanosecond all three such methods will perform that calculation and will finish at 5 nanosecond itself. You hear up to me? Then it will reach to this body where at 5 nanosecond whatever crunch was supposed to do is already done. Now it will think that it will calculate that what are the next actions. Is it after 10 nanosecond do I need to do something? Then it will increase the simulation time to 10 nanosecond, this guy, this body.
So, so
And
that would
yeah,
mean that would mean like if the crunch section took 5 nanoseconds, that
crunch won't take any time. Crunch will take zero time.
but if the real
Crunch will
execution is
schedule something which will happen after 10 nanosecond. It will say that okay, I perform something like this, but this will happen. The next thing will happen at 10 nanosecond.
so it is just a schedule. Crunch is just a scheduling policy rather than the runner itself.
Yes, runner is this body. The simulate is the
Ach- अच्छा. ठीक
and
है,
crunch
got
is
it, got it.
following is performing a certain aspects of it with respect to keeping whole system synchronized. That at given
अच्छा
time
ठीक
it
है,
will
got it.
do
वही
all these things.
वो पॉलिसी मेकिंग ज्यादा है वो.
Hmm, hmm.
Got it.
Got it. So now crunch also has two parts to it. One is evaluate and another is update. Right. So shall I go in that direction? Okay. So that's where the delta phase comes in picture, right? I wanted to explain more on the delta cycle. So what happens is, let's imagine that you have two hardware blocks connected back to back. This hardware block calculated something at one clock posage, 5 nanosecond. Do you think if the another process runs at same 5 nanosecond will get this new value? No, because both are supposed to execute parallelly at 5 nanosecond. This guy executed something won't be available to this guy till it performs its calculation. This particular small delay is what is called delta cycle, where the the value of the newer uh, uh, signal or variable will take that much time, a small time, to reach to the another guy. That particular phase is delta cycle. We'll explain more in the when I try to uh, uh, show one example of it. But how it happens is we will go there when I have some example. So let's move to this four things, right? So we saw what are runnable process. I mean, what actually mean by runnable processes, which are processes available for execution at the given simulation time. The update request for the newer values, that delta notification will happen for small time and then you will have the updated value. And the last one is timed notification, where you have to increase the simulation time for reaching to the next event. Okay, so let's look at an example of it. So this is a kind of a very basic timer IP I want us to look at. It has three interface signals. One you get as an input is a clock, another is a reset, and third one is interrupt. So Ideally, what will happen is on the clock's pause edge, you will perform some calculation, you will increment the counter. On reset, you will reset those counter values and internal variables. But the interrupt is when you raise a signal when you have whatever amount of time you wanted to spend, it's spent, you raise an interrupt. And you do it using these three registers. Let's look at match value and current value register. This current value register would be your internal counter. Match value would be the configured value. When both are matching, you will raise an interrupt. And this configure register is to start or stop the timer, and whether you want to raise an interrupt or not, interrupt enable pin. Okay, so let's look at if we have to write this in hardware, how will it look? This is a Verilog code. This is a generated code, so I don't know if it is very accurate, but it is good. So you see this input and output, clock and reset are input, interrupt is an output. You have these three registers. On each passage of a clock or on a reset, when it is applied, if it is reset, you will reset the counter, or if it's a passage of clock, your register is configured the bit 0, this one, start or stop the timer. If it is enabled, we will increment the counter. And this is a comparison of count with the match value. Whenever this match is true and the corresponding interrupt enable is true, you will raise the interrupt. Otherwise, you will deassert the interrupt. This is a very simple code, right? Now, if we have to mimic this in system C, this is how we will do. So let's look at this block, right? This is a system C code. Similar to that, you have a clock, reset, and interrupt, configuration register, match value register, and internal counter. So if you see this timer process over here, we had this always block, that always at the passage of clock you do this. Similarly, we have a timer process which runs in the clock's passage, a reset process which runs on the nag edge. A reset will reset the counters. In timer, if you have timer enabled, uh, you will do the counting. Whenever you reach the match value, you will generate the interrupt. Okay, and this is a kind of a test bench. It prints and certain things we'll try to drive. So let's run this example once. This is where we'll see how the time is evolving. So when we start the simulation using this SC start, right, neither of these methods would be ready to run because we haven't received a clock passage, we haven't received reset snaggage. But if you see here from the test bench, generating clock and we are generating the timer, so at the 0 time these two processes would be ready to run. It will execute this two at the same time, and this guy is continuously generating the clock 1010. Now in the test part, after 4 nanosecond of time, I am enabling the interrupt. I'm enabling the timer, and I'm keeping match value to 5. So after 5 clock cycles, I should get an interrupt. If you see the print, test bench is saying that interrupt is set to fall for 0, 5, 10, 15, 20. But this timer will raise the interrupt at 25 nanosecond. Let's enable when actually we started the timer. So now you will see this counting in progress at 5 nanosecond. We consumed 4 nanosecond here, then we started the timer here, but because our clock is at, let's say your passage will come at 0, 2.5 nanosecond, 5 nanosecond. So at 5 nanosecond of a timing, we started the counting. So this is when our timer process got started. So this is how we consume or synchronize various systems.
Nikit,
Yeah.
one more question. I'm sorry.
Yes, please.
In this EDA playground where we are playing with this, So the timings given here, like when we are saying that we are getting interrupted after 5 nanoseconds, is it a real clock cycle in the EDA playground? Or like is it just something that where we are calculating the clock ourselves and then saying, okay, 5 nanoseconds over?
If you see that system C code which I showed, right, where the next time and timestamp
In
was being
in
calculated,
that
this
in
is
that
that time.
in that from what I understood, in the system C code, we were generating the clock cycle, right? We were keeping a count of the clock cycle, and then according to it, like in a clock cycle, I believe one cycle would be equal to 1 nanosecond, right?
No, this is where
The,
the configuration starts. It's if you see the system C code, it's not actually tightly coupled with just the clock cycles. It is kind of coupled with time, and you can convey that how you want to consume that time. So currently, if you see the this code, I'm saying that I want to consume the time based on clock, posage, and negage, and I am in control of generating when. So let's say if I change this clock cycles, this is my clock, right, which I am generating. This the system C is an facilitator for it. So all the event which was happening at 2.5 nanosecond now will happen at 5 nanosecond. You see, 0, 10, 20. So it takes this as an event that when your clock, this clock is getting a posage. The For them it doesn't matter. For system C, the clocking is not important. The notion of time is important. So now if you see how we are enabling this timer is via notion of time, 5 nanosecond, 5 nanosecond. This is what we supply, that this is when each event will happen. So if you recall the system C block, right, we were seeing that, okay, at this much time, not clock, this much time, we had this many processes to be run. Then it will increase the time till we get another processes to be run. This is how the time is increasing. Apply that logic here, that at 0 nanosecond, this process and this process was ready to run. Neither other was ready. So at 0 nanosecond, it executed clock gen and test timer. While executing this two, it realized that my next execution is after 5 nanosecond or after 2 nanosecond. So at 2 nanosecond, it will execute this line. After 5 nanosecond, it will execute this line. So the time increased. Now let's say you reach 5 nanosecond. What will happen is at 5 nanosecond, again this guy is anyhow active, but we will got clock's posage. So even this method would be available for execution. So it will run at 10 or 15 nanosecond, three processes. If you see this particular guy, right, it will run. So this timer counting in process starts at 10 nanosecond currently, right? But if I add a print here, I'm just keeping the same print. Okay, uh, maybe let me change. So understand this as an kind of virtue of just the simulation time. So if you see timer process, because I have clock true here, it is considering that as a posage. It is running here. The next one, it is running at 10 nanosecond, 20, 30. It will continuously start executing. But you getting my point?
like right, since we are in simulation right now, so it is the virtue of the simulation itself, not a real.
Mm, yes, yes. That's what we try to mimic the hardware. We don't actually
Exactly. Yeah,
consume
yeah, yeah,
anything.
exactly. That's the exact point of modeling, right? I
True,
believe.
true. Yes.
Okay, got it, got it.
So let's make this 2.5 for now. So now what I wanted you guys to look at is when actually we got the interrupt in this block. So you see this interrupt at clock 1. I'm continuously printing when I am actually getting an interrupt. So if you see, where is this print from timer at 25 nanosecond, it says that I am raising an interrupt, right? But at the same 25 nanosecond, the test bench says interrupt is set to false. So if you see at 25 nanosecond, both these processes were ready to run. As part of this execution, this guy updated the interrupt value to true. But as I said, for that delta notification, right, both processes will run at same time, but won't be the new value won't be available for this particular guy because both ran at the same time. This guy updated as part of his process. This guy won't get the newer value. This is how we mimic the hardware, that both are executing parallel with the older values. Am I clear here? Now, does this mean interrupt was not raised at 25 nanosecond and raised at 30 nanosecond? This guy? No. Let's enable this print. And do I have it enabled? So I have one more print which says when I have raised the interrupt. So this is raising interrupt at 25 nanosecond. With clock, it will say it is false. But if you see over here, the same test bench says that this interrupt is true. In fact, at 25 nanosecond. This is because of the delta cycle it will consume. So now we are continuously mapping with interrupt here. So we are not triggering this particular process at the same time at 25 nanosecond. Actually, when we did this, the next cycle, that small time, will get consumed and then this guy will get called. This is that wires propagation in hardware. Okay, so this is a delta cycle concept, that yes, it interrupt happened at 25 nanosecond, but if you are on the same sensitivity, same time, both are starting, you won't directly get the updated value. You will get it after some time.
Um,
Then there,
so,
yeah,
Nikit, would the delta cycle represent the timing spent in the buses?
not the bus. See, usually when I'm saying this, right, that two things are executing parallelly, right? The delta cycle concept is that even though it is updated, the new value, you won't get it because we both started at the same time.
That
This particular,
that part is perfectly fine. That in a simulation, if both the things started at 25 nanosecond, that would mean multi-processing, because and they would start with the same value since they started at 25 nanoseconds
correct, correct, but it will get the updated value, but
later.
slightly later. So this is that propagation delay. Now, if you want to be true to just delta cycles, you can write a whole system which doesn't work on time, just works on delta cycles, and still it will execute. In such scenario, you are not dependent on time. You only wanted a certain kind of execution. So that capability is there. I don't think so anybody uses like this, but of course it's doable.
But
Okay, so now let me take you one more. This is an hardware topic which I want to tell next. Okay, so now over here, if you see, I am raising the interrupt, correct? And I'm saying interrupt equal to true. Let's say if I add a print saying what is my interrupts value here, it's very silly, right? Anyhow I'm setting it to true. If I check in the next line, it should be true. Am I right? Let's run it. Maybe I'll disable certain print so that it's not spammed. What happened? Uh, you see this line? Checking interrupt at, but it is showing it is set to false. How? We have set interrupt true here, but in the next line it says no, interrupt is not true. So this is where a hardware concept kicks in. Let's take an example that A is 10 and B is 50, B is 5. If I do something like this, B equal to A plus 5 and C equal to B, the answer of C would be 15, right? But in hardware, you can have something like this. This is a parallel processing at granular level itself, that B and C both are evaluated together. So what happens is B will get the value of 10 plus 5, 15, but C will get the older value of B, which is 5. So C will still remain 5. After some time, if you check B and C's value, B would be 15. So that updations do happen, but still will still be 5. This is called as non-blocking assignment. And if you see in system C, they have kept track of this level of granularity to mimic the hardware. So hence, at even though we are doing true here, if you check in the next line, it won't be true because it is still working on the previous value. This is how, maybe I can show how this is done. So when we call this update, perform update in the prim channel, it calls the update function. And this update function, you see these two values here. So one guy keeps the current value and then other guy takes the new value. And when you call the update, the new value will get pushed into the current value. So this is how that small granularity of non-blocking assignment is even taken care here. Right?
Niket, so the website, this EDA playground, is it running System C in the background?
Yes, yes, it is running system C.
Ah, oh, nice, nice. Now I get the whole. I can match the dots now. So
Sorry,
how
I
the
should have.
test bench and the design are working actually.
Yeah,
Because
I think I should have introduced that I am in system C
yeah, yeah,
compilation.
yeah,
Okay, so I hope this helps with respect to timer. So up to now we have seen Verilog code and an system C cycle accurate code, but it is still behaving same as Verilog, right? So when I said okay, we can have abstraction, what do I mean by it? So now let's look at one more code. This I'm not running it, but let's say this. So when we were executing this timer, maybe let me increase the font. And, see, on every clock pause edge, if you remember, we used to invoke this timer. Why? We know for a sure that we don't want to increase the count till our timer is enabled. This is unnecessarily wastage of each function call happening uh, with our model. Why do we want to run it? So this is where the event based simulation comes in picture. So you can say that you start this timing process only when the start timer happens. If you say the start timer is an event, and whenever somebody sets that start timer value to 1, you will notify that okay, on the next clock period you start my timer. Then this is what event based simulation is. You aren't true to now simulation time, you are true to the functionality of it. So you are not executing every time the timer process from the starting, but you are doing it when it makes sense. And let's say somebody in between stop the timer, you will say that start the timer whenever anyone start configure it to be enabled. Yes, tell me.
Yeah, Niket, I think there's a discussion in the chat box, which I think you would be able to answer better. So, like, I think the question is, do we have options in System C to set non-blocking assignments to blocking assignments like macros?
Uh, can anybody come online and explain what they mean by it?
I think Rishak Ram
Context
has
is
asked
from
the
the
question.
RTL. Yeah,
Yeah.
like I think the current, sorry, the the context seems to be from RTL perspective, where Verilog has this concept of blocking and non-blocking assignments. So
Mm-hmm.
yeah, but I don't think System C as such has like
No, race condition will happen
particular.
here too, right?
No, no, no. I think they're talking about the assignment statements, right? Like the blocking assignment or the non-blocking. So you can
Yeah.
have
So
a
I
higher
told you.
declaration you can introduce at an
So
RTL level.
let's look at blocking and non-blocking assignments. Okay. So if you are remaining true to the system C interface, if you see that interrupt pin was in fact an system C construct, right, where you can control it. Over there, you have it as a non-blocking assignment, right? You wait for a delta cycle for your next updated values. Whereas if you are using, and most of the time we are using normal C++ variables for our intercommunication, that if we perform this, we'll update our internal variable like this. It will be available to the next guy. But now over there, the same race condition will happen. Which one ran first? So it's true here as well. Getting my point?
So yeah. Actual, my question is like here by default system C is using non-blocking call. So
True.
my question is like whether is there an option in system C to set that non-blocking call to blocking call so that I don't want to use non-blocking call in my programming.
It's true. I mean, usually what I told you will happen, right? You will use your local variables. They are non-blocking. If you don't attach meaning to your system C meaning to these variables, they'll become blocking. And then, if it is a system C port kind of a thing, right? It will become non-blocking for this consumption of delta cycle and overall synchronization of the system. It is much needed for the synchronization of system rather than just having a feature.
Yeah, I got it. Yeah, sorry.
So okay, so we saw the kind of event driven this too. Now over here also there is a debate that do we actually want to be very true to the time? How about we simply consume the time based on the calculation? We can do a mathematical calculation that my current time is this. I'm supposed to raise interrupt at this time. Why do I go and every time increment a count? I'll simply schedule it after interrupt after this much time. Yes, it is doable. It can be done. It will be a single call and you will still mimic the functionality. Of course you will lose certain control of it because you are not performing something at each clock period, but that's fine. Oh, I'm sharing my screen, right? Okay, so if let's move to this. Now what I wanted to take you guys to the, now this is where the system C kind of ends and we move towards TLM. So if you see for this configurations, I've used setter getter APIs, right? But they are not standardized, not generic, and not, this is not the way how you access a register. So what is the way you access a register? In order to access a register, this is what the interface looks like. How you access a particular register, you want to provide address that okay, this is my address where I want to perform a write or a read operation. For a address, this AW address you see is, let's say, a write address. You want to have an handshake between both the guys that okay, we have received your address request, then you receive the data from the handshake perspective, and then you provide an acknowledgement. For a read, again you get the address, then the data. So what happens is Of course, it's like multiple signals communicating to you one thing, that this register this value, but you need all of this, right? If you want to be true to the interface. Now, this is too time consuming, right? Sampling all these things. Ultimately, you are interested in one thing, the address of a register and the value. So this is where the transaction level modeling comes in picture. You combine all these things in one transaction, saying this is my address, this is the command, this is the data. This is where kind of a system, C++ struct comes in picture, or a class which having each variables like this. You combine them together and you perform it as a single transaction. You can convey that this transaction will take this much time. That's there. So now we are going at a higher abstraction level, but we are doing it with ease. We don't have to sample many things just to reach one point. So I won't go much in detail over there, but this generic payload, the TLM generic payload, had the information like this. And there are standard APIs, so you don't send anything over there. We use B transport or NB transport to send this payload and receive the acknowledgement. Now, the last thing is, even after doing this, let's assume there is a memory which is continuous in addresses. You want to perform some 1 MB write to that memory, right? What will happen? You will send one B transport with address as 0, another B transport, another B transport to each of them. Ultimately, what you wanted to do functionally is update that memory location with this data. But in order to do that, you send 100, let's say, transactions. And if you have in between some other blocks such as bus interconnects, it will get multiplied by that much. So you will have that many calls kind of unnecessarily, because your intention is to update that memory. This is where advanced kind of a concept comes in, which is direct memory interface, called as DMI. It's very simple. It says that if you want to do something like this, I am continuous in my execution. Here is a pointer to you. You take this pointer, you do mem_read, whatever you want to do. This is how the systems, this Linux execution can happen in couple of minutes rather than so many time, because you got that pointer, can perform anything. And then they have enhanced, of course, has to have that if your such region becomes unavailable due to security or any other reason, you will communicate it back saying no longer this pointer is valid. You will invalidate, and you shouldn't use it further. So this is how the advanced concept of DMI is. Now this kind of brings end to my presentation. The application of the system C and TLM, of course, spans on multiple directions. First one, we saw that we want to do embedded software development, right? You will write codes which are functionally accurate, not timing wise, but they'll do what is needed to be done so that your software is satisfied. Second is architecture exploration. This is what I kind of currently work on, where we don't care about the functionality, but we care about execution of each block with respect to time. If we expect a certain, let's say, memory, we expect that memory for each write to consume 10 nanoseconds, right? And if we are performing 1,000 writes, we don't care whether the write, whatever data got put in the memory, is retrieved. What we care about is consuming of that 100 or 1,000 nanoseconds. This is what we model as part of architecture exploration, and we come up with number that if this is the system, this much time it will take for a given, let's say, the test case or the scenario. So you will be more prepared about how your performance would be. Same applies to FPGAs, which is FPGA prototyping. So for an FPGA, certain parts would be hardened. Those things we try to model. And last is, you can again mimic the similar performance with power. So if I access this many times, this much power I'll consume. You can come up with the power estimates too. So these are some of the applications I know of this front.